Hello everyone and welcome to lecture 13 of the course on quantum entanglement and non-local games. I am Dhiraj Madan and today we will be looking at C-star algebras. So in the last lecture we saw that if we want to perfectly embezzle an EPR pair starting from from 0 to EPR, and if I am allowed to use some catalyst psi, then basically a psi which is of the form HA tensor HP, this does not work as a perfect catalyst, right? So because we want to achieve this with fidelity 1, and we saw that no state in the tensor product structure works for us. The kinds of state which do work for us are of the form EPR tensored with itself infinite number of times. And such a state actually does not belong to HA tensor HP. In order to formally understand these sort of states, we need the idea of something called a C-star algebra. Okay. So essentially, in order to motivate C-star algebra, let's look again at operators on linear spaces, right? Operators on vector spaces. So suppose if we have some vector v, we can define a notion of a linear operator which basically acts on v and gives me an element from v itself. So such an operator also satisfies t of alpha u plus v is alpha to tu plus tv, right? So this is essentially the linearity property, right? So we need to look at the class of linear operators on vector spaces. Now if I take two linear operators t1 and t2, then I can even add them to get t1 plus t2, which is also going to be a linear operator. Not just that, I can even compose two linear operators in order to get a linear operator. And if I have some element in the scalars, so typically our scalars are complex numbers, right? Then alpha times t is also a linear operator. If I take addition and the scalar multiplication, then essentially they will form a vector space, right? And if I take addition and composition, they will together form a ring, right? So a ring, if you remember, consists of two operations, addition and multiplication. Over addition, it forms an abelian group. With multiplication, we have the property that multiplication is associative, right? And multiplication distributes over addition both left and right way, right? So it's essentially a ring and a vector space, and if you have a structure which is a ring and a vector space together, then it's called as the structure is called as an algebra, right? And note that when I say that it's a ring and a vector space, both the addition operation of the ring and vector space should be common. Okay, so I can't have a separate addition for vector space and a separate addition for ring, that I cannot have. But our operators are not just operators over any vector space. These are operators over Hilbert spaces. So operators over Hilbert spaces, in addition to having a multiplication and addition and a scalar multiplication, they also have a notion of conjugation and norm. So a conjugation operator will map t to t star, it's adjoint, and norm operator will give me the operator norm, right? And there must be some properties which are consistent between these four sort of classes of operations we have seen: vector space, ring, conjugation and norm. We will just see what these are as we formally define the notion of a C-star algebra. So formally, a C-star algebra A is a set with the following properties. Firstly, it is indeed an algebra So which means that it is a vector space along with the multiplication operation such that for multiplication it forms an it is associative, and also multiplication essentially distributes over addition, and this distributivity must hold both ways, left and right. Okay, so essentially what we are saying is that by ensuring that it is a vector space, I have already ensured that there is an addition operation in which it forms an abelian group, and now additionally I define a multiplication operation. This gives it a ring structure. So overall it becomes an algebra. And note that this addition is same as the addition from the vector space. Right. Now next property is that A must have a star map So the star map must satisfy that A star star must be A. Also A plus lambda B star must be A star plus lambda conjugate B star. Right. So we are now seeing, okay, the star when it acts on itself, when it acts twice, we get the same element, right? So this is what we expect from any conjugation operator. And not just that, we also discuss, under the vector space operations, how does star act. So under addition, it just goes over addition, but over scalar multiplication, it conjugates the scalar coefficient. And over the ring structure, it behaves as AB star is B star A star, right? So this is for all AB in algebra and lambda in C. Okay. Now, if you satisfy 1 and 2, right, so basically an algebra which has a star map, that is called as a star algebra. But what we are talking about is something more, which is a C star algebra. So let's see what is another additional thing we have. The next additional thing we have is that it must also have a norm. Now, what does this norm satisfy? So this norm must be an operation which satisfies that, firstly, norm of any element is non-zero and norm of an element is 0 if and only if A is 0, right? Secondly, we have that norm of any scalar multiple is mod lambda times that norm of A. Right? So these are the properties which we usually expect from a norm operation. And norm of A plus B is less than equal to norm A plus norm B. So this is the triangular inequality, this is the scalar multiplication, and then you have the non-negativity. And additionally, A is complete with respect to norm. So in general, if you have these conditions, then you actually get a Banach space. But here additionally, since we also have an algebraic structure, we also need that norm of AB must be less than equal to norm A times norm B. Right? So this essentially is again motivated from the theory of operators, wherein we have that norm T1 T2 for any operators T1 and T2 is less than equal to norm T1 times norm T2. Right? So an algebra with such a norm is called as a Banach algebra. So if you have 1 and 3, so that is you have algebraic properties and you have these properties, then you get a Banach algebra, right? And fourthly, what we have is that together, if I take norm and star, together they satisfy that norm of A star A must be equal to norm of A square for all A in A. Okay. So this is the additional one more property we have seen. So together these four properties define a C star algebra. If additionally we have a multiplicative identity, right, for the ring multiplication, then what we get is a unital C star algebra. For us, most of the C star algebras which we will be using are going to be unital. So let's look at some of the examples. So one example we have already seen is the notion of bounded operators on a Hilbert space, and this was indeed a motivating example for defining C-star algebras. These are binary bounded operators over some Hilbert space H, right? Now, what do you mean by a bounded operator? So, an operator A is bounded if the norm of this operator is supremum over all states psi in H such that norm of psi is 1, norm of A psi, this is less than infinity, right? So, in this case we say that this operator is a bounded operator, right? So, a homework for you is to firstly check that BH is a C-star algebra. The class of bounded operators is indeed a C-star algebra, right? So, we have already seen the addition operations, the conjugation operations, these all exist on our operator space, on bounded operator space, and we also have a notion of a norm, right? So, we can talk about the operator norm, which we have already discussed, which is the supremum over all states psi, which has norm psi equals 1, norm of A psi, right? So, we already have an operator norm, and we just need to check that all the conditions which we defined are satisfied, right? So, norm, conjugation, vector space, ring multiplication, they are all consistent with each other, right? And you can go even a step further, right, and see that any subset, so any subset S of BH that is closed with respect to algebraic operations and norm. So, by meaning that it is closed with respect to norm, we are ensuring that it is closed in the metric space sense, right, because we actually need a complete metric space always. So that is why we need a this closure property. So, this is a C-star algebra. So, this is something which we will have to show. The second example which we discuss now, so this is the homework for you. So, most of the things, you know, while defining the C-star algebras I already motivated, so just you have to check the few things, okay. And note that when I say star operation, the star operation which we will choose must be the adjoint, and the norm operation which we will be choosing is the operator norm, okay. So, let us since now in the second part I talk about a subset which is closed with respect to algebraic operations and norm. So, actually we will now try to define something like that. So, the example which we take is called as CAR algebra, right. So, CAR refers to canonical anti-commuting relations. Okay. So basically we need to construct CAR algebras in terms of infinite tensor products of Pauli operations with finite weights. So, let us see what this means. So, basically what we will say is that, okay, so what are the Pauli operators we have? So, single qubit Pauli operators which we will choose will be identity X, Z and XZ, right. So, XZ is something I will define as W. So, I will call XZ as W. So, I am not taking Y, but I am taking XZ, and it only differs via phase of iota, right, because Y is iota XZ. Now, what are Pauli strings with finite weight? So, basically these are tensor products of these Pauli operations, right? And what I'm going to talk about is infinite tensor products with finite weight. So what does this mean? So basically I can take an infinite sort of product, tensor product, so basically I have, let's say I have I tensor x, tensor w, tensor I, tensor z, tensor I, tensor I, tensor I, dot 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 dot. So after a certain point I have all identities. So the weight of a polystring is defined as number of non-identity elements. When I say I have a finite weight, then it means that up to some length I have these non-identity operators. In our case we only have 3 non-identity operators. After that they are all identity. So I have I tensor x, tensor w, tensor I, tensor z, and then all i's, right? So the ones which contribute to weight are these x, w, and z. So the weight of this thing, so let me call this p. So weight of p is now 3, right? Because after z, the final z, all these are identities. So we are only talking about now we are talking about infinite tensor product of polys, but we will be talking about those infinite products where there is a where basically there are only finite number of non-identity terms or finite weight operators, right? So we can denote such operators okay, so we can denote them by xa zb, right? So I can say, okay, on which bit strings I have an x and on which bit values I have a z, and just I keep an indicator for those. Okay, so for example I can write this xa as xa1 tensored, xa2 tensored, xa3, and so on. So note that this is actually a1, a2, a3, so on is actually an infinite sequence, but only a finite number of non-zero values. So after a certain point I know that everything is going to be 0, so I can actually indicate it via some finite sort of string also, and then I have this much times, and then I have some values on z, zb1, zb2, zb3 up to so on. So I can write it as g as xazb, where a and b are both finite dimensional strings, right? Because the trailing zeros do not matter to me, so I can only take it's fine to take the finite size string also, right? And here C of g is essentially the all the possible complex linear combinations of these operations, right? So finite sums with coefficient in C. So you need to check one thing is that C of g is closed under multiplication, and under conjugation also. So you should check that. So under addition it will be closed because it consists of linear sums, so it will be closed under addition, but it will also be closed under multiplication and star. Okay, and now we haven't yet defined a norm, right? So let's define a norm. Okay, so for all a in C of g, right, so there is going to be some integer after which all the elements are identity. So I can what I can do is that I can combine the first m elements. So suppose if there are only after first m everything is identity, so I combine the first small m elements, and this matrix capital M is going to be in C2 to the power m cross 2 to the power m, right? So say all terms are identity, after first m. Okay, now why am I doing that? Is that because I need to define a norm, right? So how do I define a norm for infinite string? So first I identify the first part of it, after which everything is identity, and now I define norm A to be just this norm of M, right? Because this is a finite dimensional matrix and I can define a norm for this thing, right? And now I have already defined a norm, so you can check that it satisfies all the properties of norm, which means that it should satisfy triangular inequality, it should satisfy scalar multiplication property, it should be non-zero, it should be 0 if and only if this string is 0. But additionally, we also have that norm AB is less than or equal to norm A times norm B. So, but apart from that, you also need to check that it should be actually complete metric space, right? Because then only it will give me a Banach algebra. But now it may look that it is not, but so what we'll do is that we define CAR algebra to be the completion of CG under this norm. So in operator theory, we can always, suppose if you have any metric space which is not, complete, you can always extend it to a smallest metric space which is complete and it contains this given metric space. So such a space is called as completion. So we can define a completion of this CG space, and that will give me the CAR algebra, right? And now here, until now I was using Z as the indexing set of these poly strings. So I have the 0th element, first element, second element, typically how we define qubits, but we could have also used Z, right? So basically I can define them as doubly infinite strings. So basically there is a middle element 0 and then there are elements to the right and then elements to the left. So can even define indexing set to be Z instead of N. So here basically then we will have two-way infinite strings. Okay. So for example, I can have some element which is say of the form X tensor, I tensor, Z tensor, I tensor, I tensor, I dot dot dot. So after this set there are all i's, but then I can even go left, right? So I can have xz tensor, x tensor, z tensor, I tensor, I tensor, I. So I can have infinite number of identities to the left and to the right. Now we can even define the notion of positive elements. So this is what CAR algebra is. You may pause the video and just try to revise this again. Now coming back to the general idea of the C-star algebras, so we can actually talk about positive elements. So an element A in this algebra is positive, that is A is greater than or equal to 0 if there exists B in A such that A equals B star B. So basically we are trying to generalize the notion of these positive operators to general C star algebra. So on bounded operators we know that an operator is positive if psi at psi O psi is always greater than or equal to 0 for all psi. But here and a property is that an operator is positive if and only if I can decompose it. I can decompose an operator A as B dagger B, right, or B transpose conjugate B. So here essentially that notion of transpose conjugate refers to our conjugation operation. The adjoint of operator refers to conjugation here, and that's using that same necessary and sufficient condition for an operator to be positive, for a bounded operator to be positive. We can actually define a C star element to be positive, which is that if there is some element P such that A is B star B. So this definition also agrees with our definition on B at the space of bounded Hilbert space, and that is our motivating. That's the motivation for this definition. Okay. Now, next topic which we talk about is the notion of star isomorphism and star automorphism. So essentially, a star isomorphism from A1 to A2 is a map pi from A1 to A2 that preserves the algebraic structure and the norm. So what it essentially means is that pi of a plus lambda b must be equal to pi a plus lambda times pi b, okay, and pi of ab must be equal to pi a times pi b. So it is like a vector space homomorphism. It is also a ring homomorphism, and it is also star homomorphism, right? Pi a star is pi a. And finally, norm of pi a must also be norm of a. So you might be thinking, okay, we haven't yet ensured, I'm calling it an isomorphism, but have I ensured it is 1 1 and on 2, right? The thing is that by ensuring that norm pi a is norm a, I have ensured that like norm of pi a. So pi a is 0 if and only if a is 0, right? Just from this condition, norm pi equals to norm a, right? Because pi a is 0 if and only if norm pi is 0, which is if and only if norm a is 0, which is if and only if a is 0. So here definitely we'll be able to ensure that pi is injective, right? And now it's an isomorphism onto its range space. So when I say isomorphism, it is isomorphism onto its range space, right? Now you need to check that. Okay, so basically I've already given you the answer, but just try writing it yourself, homework. So show that star isomorphism must be injective. Okay, now given that we have defined a notion of star isomorphism, we have a very interesting theorem which is called as GNS theorem. So this GNS, the initials stand for Gelfand, Naimark and Segal. So what this theorem says is that for any C star algebra A, there exists a Hilbert space H and a star isomorphism pi from A to bounded operators on H. So this theorem is called as the GNS theorem, right? And now once we have defined the notion of the star isomorphism, we can move to the notion of a star automorphism as well. So a star isomorphism is nothing but a star isomorphism from A to itself. So when we say we have an isomorphism, I said that from A1 to A2 I can have an isomorphism, but if A1 and A2 are the same, then it becomes a star automorphism. Now one good example, one common example of the star automorphism is a conjugation map. So suppose if I have any unitary element, okay, What do we mean when I say I have a unitary element? Well, I mean that u star u equals u star equals to identity. That's what I mean by unitary element. Then given this unitary element, we can define alpha sub u from A to A by alpha u acting on A as u star A u, right? So a homework for you is to check that this satisfies all properties of star isomorphism. Right, this conjugation map alpha u equals u star, alpha u of A equals u star A u, you have to check that it satisfies all the properties of a conjugation map. Okay, so this is the homework for you. Okay, so you have to check. Okay, so how it satisfies, you know, all these, that like a pi of A plus lambda b is pi A plus lambda pi b, pi a b is pi A, pi b, pi A star is pi A, and norm pi A is norm of A. So actually, okay, so here it should be pi A star equals pi A star. Yeah, so this was a small typo. Yeah, correct that. So that's it for today. Now in the next few lectures we will see how, using this notion of C star algebra, we can define, you know, appropriate states which allow us a notion of perfect embezzlement. Okay, thanks a lot. Bye.